So today let's start. The question is determine the magnitude of the couple M required to maintain the equilibrium of the mechanism shown in the figure. So which is this couple M is required. We use principle of virtual work to solve the problem. I said P is external force applied on the mechanism. Sorry for that. So today I'll give a disclaimer that today's internet is not very stable. I don't have very stable internet, so it might fluctuate with this a lot. Please bear with me. And I guarantee that this lectures will be on YouTube. So if you miss something during the talk, you can get back to YouTube and look at the solutions there also. I'm really sorry about the internet connectivity for today. Please bear with me. So if you look at this problem here, this system, if you apply a force P like this, so this part, this EB part will try to go and flatten like this, right? So to maintain it, you need a couple M, and you have to solve it by using very important principle of virtual work. Principle of virtual work. So what is principle of virtual work? The principle of virtual work is at equilibrium the total work done on the system would be equal to 0. Now what is the total work done then? Is this couple, and if you want to move this by delta theta amount, then this is the work done due to the couple plus this P, and if this P is creates a dx or delta x amount of displacement, then it is P delta x. So this is the work done. So if this is 0, so the couple becomes P delta x delta theta. Now for delta theta tends to in 0 limits, this couple becomes P dx d theta. So this is the couple. So what is this? We have to find out the change in x due to change in theta. This is what we will have to find out. So let's say this is delta x, this is our x direction. Okay. Now how will we find out? So due to this, so let's draw the free body diagram. So let's say this is A, from here we have D, so A, this is F, this is E, B, so this is the direction of the force P, and we have D here, and this is the free body diagram for this, and every length is L. So this angle is theta, let's say, and also this angle is theta. Now for P, the total we have to find out the, let's find out total displacement along x direction. So let's say this is x direction. So first is this length, right? We have to find out this length. So let's name it M. Let's name it M, and this is C. So in this triangle, if you look at this triangle, we can write AM by AC. So this is also theta. So this is, no, sorry, sin theta, right? Sorry, this is not theta. Sorry. No. Sorry. This is actually theta. So MC by AC. We want to find out this length, not AM. So this is basically cos theta. So MC equals AC cos theta, which is equals to L cos theta. First thing. So we found out this. Next, let's try to find out this length. So let's draw a perpendicular like this till n. So what is this? From here we can have this angle to be theta. So from here we can write Cn by Cf equals cos theta. So Cn equals L cos theta. Similarly, we can find this Nd equals also L cos theta. This is L also, right? So total displacement in x direction, total displacement along x direction, which is, let's say, right at x, is MC plus Cn plus Nd. So MC plus Cn plus Nd, which is equals 3L cos theta. Then dx d theta becomes minus 3L sin theta. Fine. So M, the couple M, becomes P dx d theta, which is equal to minus 3LP sin theta. That is our answer. This is the answer. So sorry, there has to be a minus sign here. So this becomes plus. So 3LP sin theta. Okay. Fine. Okay, let's do the next question. The spring constant K, so there is a spring like this, is unstretched when theta equals 0. So when it is like this, and this rod AB is like this, then draw table like this, like if this theta equals 0, then it is unstretched. Okay. What is the expression of force P in figure? So this force, what is the expression of force, is required to deflect the system at an angle theta. The mass of the bar is negligible, is principal or virtual work to solve for the system. So let's say this is the x direction and this is the y direction, like this. So we have force P here. This is the force P. Now let's assume due to this force the displacement along x direction is there is a displacement along x direction which is x, okay, and there are displacement, so for here, and what is the total displacement along y direction. So along x direction we have x equals L cos theta, or let's say this is y, so the total displacement along y direction, y equals, so let's say the whole thing is y, so L sin theta, so x is sin theta and y is L cos theta plus L cos theta. So this is L cos theta, this is also L cos theta, so it is 2L cos theta. Okay. Now the change, so we have to find out the change in the length in y. So what is the change in length in y? So delta, so this is what delta spring is. So delta spring means the displacement and the spring. So this is y at theta equal to 0, which is unstretched, which is theta equal to 0, minus y at theta. So y at theta equal to 0 is 2L minus 2L cos theta. Okay. Then spring force is K times delta spring, so which is 2L K 1 minus cos theta. So principle of virtual work. Now let's apply the principle of virtual work. So what will be the principle of virtual work? The total work done in the system should be 0. The total work done is force along x direction times displacement along x direction plus force along y direction times displacement along y direction, delta y. So from here we can write dx equals L cos theta d theta. So what we wrote from here, we wrote dx equals L cos theta d theta. Then so P dx PL cos theta d theta plus this spring force is T1 K to 1 minus cos theta, so this spring force, and delta y or dy becomes, so from here, so dy becomes minus 2L cos theta minus 12 sin theta d theta. Okay, so minus 2L sin theta d theta, so which is equal to 0. For non-zero d theta, it becomes, let's solve it. So PL cos theta plus, so this becomes minus 4 L square k 1 minus cos theta sin theta equal to 0. So 1 L gets cancelled out, P becomes 4 L k 1 minus cos theta sin theta by cos theta, which becomes 4 L k tan theta minus sin theta. So 4 L k tan theta minus sin theta. Fine. So cylinder of mass 10 kg suspended by a spring of stiffness 2 kilonewton per meter. Okay. X be the displacement of the spring from its equilibrium position. Assume this determine the total potential energy of the system. So what are the we have to find the total potential system. So what will be the contribution? One is spring energy, and this whole thing there is gravity, so it going down because of gravity. So the second one will be gravitational potential energy. Okay, so gravitational potential energy. So spring energy is, we all know, half kx square, and gravitational potential energy is mgx. This is the form. Now we have to decide the sign. Hold on, let the screen come back. Okay, now to let the sign. So we know the higher from the, so let's assume this is the ground. This is the ground. Now the higher from the ground you go, the gravitational potential energy will increase. The lower you come, it will decrease. So what will happen is, if you are at this height, whatever the gravitational potential energy is, if you go x height lower, it will have less gravitational potential energy. The total energy will be this spring energy minus mgx. So whatever the answer is, so only if you look at the questions, these two cannot be, because spring energy has a negative sign, it's not going to have a negative sign. Only this first option, this has gravitational energy as negative. So this is the answer. So this is how we do question 3. Now question 4. So in question 4 it says the uniform link AB has a mass m. So this link AB has a mass m, which makes an angle theta with the horizontal. Its left end edge travels freely in the fixed horizontal slot end B is attached to vertical plunger. So this B is attached to vertical plunger which compresses at the spring as B falls. So if the B goes downwards, this spring gets compressed. The spring would be uncompressed at the position theta equal to 0. So if this B at is horizontal, then this is most uncompressed. Determine the angle theta for equilibrium. So you have to determine the angle theta. So let's assume the vertical displacement here is y. So the due to this compression of P is y. So due to the compression, the spring energy will be half k y square. Okay, and there will be gravitational potential energy is mg y center of mass. So this is our center of mass. So whatever the center of mass has traveled, so y is the position of P point and this is center of mass. So whatever the center of mass has traveled, that will be the mgy. Okay, now if we look at it, so let's say horizontal is the y is base. Now this is y. So what is y by AB? Is some sin theta. So y equals L sin theta because AB equals L. Okay, so y becomes L sin theta. Now I'll redraw this picture for you guys to understand it easily. So I am drawing this whole thing is y, but the center of mass is at L by 2. This whole thing, this thing is y center of mass. Okay, so this is our theta angle. Fine. So basically this is A, this is B, and let's say this is O. So from here we can write y center of mass is L by 2 sin theta, half of it. So if this is L sin theta, this is L sin theta, it is this y center of mass is the half of it. Okay. So to calculate it, you can write it like P. So then PB becomes L by 2 sin theta. So then OP becomes L sin theta minus L by 2 sin theta, which is L by 2 sin theta. If you want to have proof. So we have y equal to L sin theta, and this y center of mass we have found L by 2 sin theta. Okay, now the total energy is half k y square minus mg y center of mass. Why? We have explained in the previous example. Now half k y equals L sin theta, so L square sin square theta minus mg y center of mass equals L by 2 sin theta u. Now so they are asked find theta at equilibrium. Find theta at equilibrium. So for that equilibrium condition is du d theta equal to 0, which gives u first is k L square sin theta cos theta minus mg L by 2 cos theta equal to 0. For cos theta not equal to 0, Why cos theta? Because theta cannot be pi by 2. This is an impossible angle. It cannot go because the spring would not let it go. So what will happen is cos theta gets cancelled out. Sin theta becomes mgl by 2 by 1 by k L square. This gives sin theta equals mg by 2 kl. So the answer is mg by 2 kl. Fine. Okay, let's go to the next problem. So it is about friction. It says that homogeneous cylinder of mass 30 kg and diameter 400 millimeters. So we have given mass 30 kg and diameter is 400 millimeter, which is 0.4 meter. So radius is 0.2 meter. Okay. Against the vertical or inclined surfaces as shown in figure. Keep the coefficient of static and kinetic friction between all surfaces is 0.2. So mu equals 0.3 coefficient of friction. Determine the clockwise couple M with the which would cause the cylinder to slip. So clockwise couple M is the radius of the cylinder plus the total force acting. So total force at this point and this point, because it wants to rotate. Okay, so in this, let's say you are here, so it tries to move like this. So there is a normal reaction, and there is a friction, and there is a force F1, frictional force like this, and this is the normal reaction. So let's say this is x direction, this is y direction. So in x direction, the normal reaction in x direction, so let's say the component of normal reaction is n1. So x direction, what are the forces? The component of normal reaction plus the component of force minus the normal reaction n2, like this. This is n1 and this is n2. Let's say this is n1 and this is n2. Okay, so then this is in x direction. So from x direction we can write n1x is n1 sin theta, because this is theta. So this is theta, this is 90 minus theta, so this is n1 cos theta, so n1 sin theta, plus n1x is n1 sin theta. So f1x is mu n1x minus n2 equals 0, implies n1 sin theta plus mu n1 sin theta minus n2 equals 0. So this gives n2 equals (1 plus mu times n1 sin theta). Now we'll do the same in y direction. So in y direction, what we have is n1y plus f1y plus f2 minus mg equals 0. So n1 y component, if this force is y component, and this force, so there is there is mg like this, and this f2 is there. So frictional force f2 minus mg equal to 0. So this is we can write 1 plus mu n1 cos theta from this 2 plus mu n2 minus mg equals 0. So this gives n1 equals mg by 1 plus mu n1 cos theta, and we got n2 plus mu n2, which gives mg by 1 plus mu n1 cos theta plus 1 plus mu n2, like 1 plus mu times mu n1 sin theta. So the moment is r f1 plus f2, so r mu n1 plus n2. Okay, so from here you know r, you know mu n1 n2. If you put n1 and n2, I think you get this answer. Just put and put all these values together and you will get the answer. Okay. A homogeneous rectangular block of mass m, width b and height h is placed on a horizontal surface subject to horizontal force P, like force P, which moves the block along the surface with a constant velocity. The coefficient of kinetic friction between the block and the surface is mu k. So actually this should be like mu k. So the coefficient of kinetic friction between the block and the surface. So here determine the greatest value which each may have so the block will slide without tipping over. So the block might tip over like this due to this or like this. So what is the height h for it would not tip over. So if it is tipping over, you already know there should be some kind of moment balance, so moment due to P, at height h, which is m1 equals ph. Simple. Okay. Now due to its weight, what is the moment here? So here this is the line of action mg, and this is the normal reaction, and we have force. Okay, frictional force here. So if it is moving along this direction, frictional force will be along this direction. But for the tipping over, so moment due to weight of the block m2 is, so mg times, so this is the radius, the half of its radius, we will take b by 2, because when it tips over, the axis will become half of it, this breadth, so b by 2. So this should be equals m1 equals m2 for not tipping over. So pH equals mg b by 2. So H equals mg b by 2h. No, sorry, mg b by 2p. 2p. Now we have to define, just write p. P is the force. Okay. So this p equals mu n. This is the so for equilibrium, same amount of force will be there. So mu n, and this n equals mu mg. So n and mg will be balanced. So H becomes mg b by 2 mu mg. So finally H becomes b by 2 mu or mu k. So b by 2 mu k. This is the answer. Okay, so let's go to the next question. So it says a block of mass m is positioned. A block of mass m is positioned underneath an overhang that makes an angle beta with the horizontal. You apply the horizontal force mg on the block as shown in the figure. Assume that the frictional force between block and overhang is large enough to keep the block at rest. Okay, if the coefficient of static friction is mu, for what range of angle beta the block should remain at rest. So we have to find out equilibrium. So let's say this force, the force applied is mg. Then you have the actual gravitational force mg. Then you have the normal reaction. Then you have the frictional force. So what is the component along this line? So let's say this is our x direction, this is our y direction. This is beta. You can show that this is also beta. Okay. Now, and this is also beta. So for your understanding, I will just copy this whole thing. it in this free body diagram. Fine. Now along x direction we have this frictional force, or due to frictional force, minus F of cos beta, because it will be in negative x direction, plus what else is there? So this force is there, mg force. So in this direction, let's say this is F, so plus F plus. So this normal reaction will have a component like this, so minus n sin beta. Fine. So Fr so this is the force balance along x direction. Now for force balance along y direction, what will you get? So for frictional force you have Fr sin beta plus due to this you have n minus n cos beta. So minus n cos beta due to this normal reaction, plus so minus mg equals 0. So this is force balance along y direction. This is force balance along y direction. So now let's let's find out what is the so let's just change the locations a bit. So minus Fr cos beta minus n sin beta. This force is negative signs, so plus minus F equal to force, and Fr sin beta minus n cos beta equals mg. So let's divide these two. Let's divide these two. You get minus Fr cos beta minus n sin beta by Fr sin beta minus n cos beta equals F by mg. Okay. Now this frictional force we can write them as mu n, right? So minus mu n cos beta minus n sin beta by mu n sin beta minus n cos beta equals F by mg. So n gets cancelled out from up top and bottom, and we get mu cos beta minus sin beta by mu sin beta minus cos beta equals F by mg. Oh, also F equals mg. Or could we forget? So this is 1. Let's cross multiply. So mu cos beta minus sin beta to mu sin beta minus cos beta. So we have to find out mu. We have to find out in terms of tan beta. So let's take sin beta common, and this 2. So mu plus 1 cos beta equals mu okay, so here I think I missed a sign. So this is plus, or I think both of them are minus. This is also minus. Okay, I think there were some sign show. So this will be plus if we take these two as negative. F is in this direction, so F is plus. This becomes minus. The whole upper part becomes plus. Plus 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 plus. So then becomes mu plus 1 cos beta equals mu minus 1 sin beta. So tan beta becomes mu plus 1 by mu minus 1. So this is the correct answer. Okay, just 5 minutes break. I'll come back. Okay, so last question is 6.5 meter ladder AB. So you have a ladder like this. You have a ladder AB like this, and assuming the coefficient of satisfaction mu to be 0. So here the mu is 0, 0. At B, determine the smallest value of mu at A for which equilibrium is maintained. So you have to find the smallest value at A for which the equilibrium is maintained. Fine. So you have h equals 6 meter. So let's say this is h. Then let's say you have x. This is x, which is equals 2.5 meter. And then there is L equals 6.5 meter. Now in this point you have some, so this was x, remember. So the weight, the gravity mg works like this, and here it wants to slip like this. So force, frictional force is acting this way, and there is a normal reaction at A. Let's say this is N, and there and here you have frictional force equals Nb. So here you can simply write the mg should be balanced by this normal reaction, normal force, and this Na equals frictional force by mu, right? So mu becomes frictional force by mg. Okay. Now again here there is normal reaction Nb, but there is no frictional force. Also in along x direction, this F frictional force and this Nb should balance. So this frictional force should balance with Nb. So mu equals Nb by mg. So we have to find out what is Nb. That is the question. Mg we know. Now our job is to find out what is Nb. So Nb means normal reaction at this point B. Okay. So what is Nb? So we will get Nb from moment balance. What is moment balance? So this, due to this Nb, due to this force Nb, the whole in y direction about this point, it is Nb times h. This is the moment, and this should be equal to, because of the weight, this mg, and in this x direction it is mg x by 2, the moment due to this is moment due to gravity, due to weight, and this is moment due to non-friction N. Okay, so So from here NB we got mgx by 2h. So mu becomes mgx by 2h by mg. So mu becomes x by 2h. So x is 2.5 meter, h is 6 meter. So 2.5 by 2 into 6, which is 2.5 12. So 0.2. So the coefficient of friction has to be 0.2 for this equilibrium to be present. Also, that was the previous year questions for previous year assignments for week 5. Hope you find this useful, and since there is no one in this year, no one joined today and there is no more questions, I would finish it here and end it in today's class here. Thank you.